So I think you can remove your mask, otherwise you never hear me. Well, it's dangerous.
I don't think so. Okay, good morning, everyone. My name is Gonzalez, and I'm going to present the Galerkin method for the Stokes problem. This is a joint work with Giro and Flash from Sorbonne University, and was started when I was visiting the laboratory reunions last year. Well, so the outline of the talk is as follows. I will present the first Stokes problem, which is very well known. Then I will describe the discretization of the problem by the enriched Galerkin method. I will present our posteriori paper, and then I will give some details on the implementation and show them the numerical results. And finally, I will get the questions. So the model problem is the Stokes problem, the Stokes equation to the homogeneous field of boundary conditions. We look for the velocity and the pressure P compressible Newtonian fluid, such that we satisfy the linear momentum equation and the compressibility equation. Here mu is a fluid viscosity that we assume is a positive constant, and F that we decide on the then we have the homogeneous field of boundary condition where G is the prescribed velocity. That is assumed to satisfy this correlation, that is necessary to ensure the existence of that. Where N is the of our normal to come. And finally, we reduce this condition to a zero condition on the pressure level in order to have the increase. For simplicity, we're going to assume that the Omega is a boundary connected polygon in Node 2 or a elliptic polygon in Node 2. So it's well known that when the volume forces are square integratable and the prescribed velocity is the prescribed motion in H1, this problem is a linear solution in H1 with a velocity in H1 and a pressure in H2. So in order to solve the problem in practice, we're going to consider an EG scheme, which is a variant of the discontinuous Galerkin method. For simplicity, we are going to consider a regular partition of Omega made up of triangles between 2 or the quadrilateral between 3. That the method works also on quadrilateral and hexagonal measures. So first, we will consider this space until a fluid of discontinuous piecewise polynomials with degree at most k, and also this other space and one sphere of fluid which consists of globally continuous piecewise linear functions over the edge. Then the enriched Galerkin space is composed by these functions which are the sum of a globally continuous piecewise linear function as a piecewise constant. So before showing you the scheme, I will introduce some notations that are usual that are common in the area of discontinuous Galerkin methods. We will denote in braces the average between two elements. We will have the
Edge. An edge.
The edge of the face to two elements. And the jumps are denoted in brackets. And it's important that we have a multiplier that fits orientation in the final. We also consider the usual norm for the enriched Galerkin space. Here, sigma e are some of the maximization parameters and we will define the data. So the enriched Galerkin scheme consists in finding an approximation of the velocity in range and an approximation of the pressure satisfying the set equation. So the approximation of the velocity is a globally continuous piecewise linear polynomial with a piecewise constant. And the pressure is a piecewise constant. The linear form A epsilon is a usual form used in discontinuous Galerkin methods to approximate the diffusive term. And for different values of epsilon, we get different average. For example, when Excel plus minus one, we have the symmetric inverted kinetic Galerkin method. For Excel one, we have the non-symmetric inverted method. For Excel two, we have the incomplete inverted kinetic Galerkin method. And for the parameters in line are the demonstration parameters and are chosen independently of each. And usually large enough so that in the linear form they get some data. On the other hand, we have that the form is the approximation of the Galerkin term. Because of this third term, that it is a consistency term that is introduced in order to ensure this scheme. This scheme was introduced by Shaban, Gilroy, and Thompson, and they showed that
About the sound is not clear for the people because they are too far from the mic.
Is
There are
that-
some remarks to speak that they cannot hear you.
Ah,
You speak too low.
il faut parler plus fort. You speak.
okay, so
Reste près du micro. Yeah, yeah.
okay, so
So please go.
is that okay?
Yeah,
Yeah,
I
so
will try to.
what Shaban, Gilroy, and Thompson proved, it was that under some conditions on the mesh, there are uniform discretization condition is satisfied, and that's the enriched Galerkin scheme has a unique solution. This condition is that every element has no more than d internal normals, that is no more than 2 internal normals in 2 dimensions, no more than 3 internal normals in 2 dimensions. For example, this element is okay, and then this another is not.
Reste ici. Go here, otherwise.
Due to the presence of the 4 internal normals, okay? So this method presents several advantages. For example, it locally preserved mass. And when compared to the preserved elements and synthesis, it has the advantage that the degrees of freedom are the global values. And it also works on polyatomic sativa, as I said before. And on the other hand, when compared with standard first order discontinuous Galerkin methods, it requires less degrees of freedom, as can be seen from this table. The same is especially great in 3 dimensions. So for these reasons, we decided to develop a posteriori error analysis for this method. So we derived a posteriori error indicator and implemented the method in different aspects. Well, the idea of the proof is quite technical, so I guess we'll give you some ideas. First, that we assume that the solution is a bit more smoother than usual. In order to give sense to the Galerkin orthogonality and consistency properties that are usually used to prove or to develop the posteriori error analysis. We also followed some ideas from Galerkin and Pascal for the discontinuous Galerkin and posteriori error analysis. That the approximation of the divergence term is different because in this case we have a different form. And finally, to control the error in the pressure, we use the continuous input condition. It's important to remark that we don't need in the posteriori error analysis in the discrete input condition. So we defined several posteriori error indicators. First, the volume momentum error, which takes into account the error in the linear momentum equation. Here, FH is a piecewise polynomial approximation of the volume forces. Then we have the divergence error and also the pressure jumps. Here, this is the set of internal edges or faces of the triangulation. We also have the interior jump of the velocity, the interface jump of the momentum, also defined on the same set of internal edges or faces. And finally, the boundary penalty error of the velocity, which is defined on the edges or faces on the boundary of the mesh. So we took these 6 error indicators and defined for each element in the mesh, the corresponding local error indicator, which is called eta. So eta is consists of the volume momentum error, the divergence error. Then we have these errors on internal edges or faces multiplied by this factor because each edge or face belongs to two elements. And finally, this term on the moment. So we prove that eta can be used as a reliable a posteriori error indicator to measure the error both in the velocity and the pressure, which is given by this upper bound of the error. And using the localization technique with Numerical, we also prove that this a posteriori error indicator is locally efficient. Here in this bound, omega E is the union of all those elements that are that share at least one edge or face with the element E, and pH is an interpolation operator of this constant. So we implemented this adaptive algorithm based on this a posteriori error indicator in a parallel code in different class. I don't know if you can read it well, but well, here we have the definition of the problem in 310. So the main thing, the main characteristics is that since the functions in the enriched Galerkin space are composed by a sum of a function which is globally piecewise linear and a piecewise constant, we consider two components for the velocity. So that here V1 and V1 are these continuous piecewise linear functions, and V2 and V2 are piecewise constants. So pressure V is piecewise constant. Then in freeform, there are functions to implement the averages, which is the mean function, and the jumps, which is the jump function, but the jump is not defined as in the field. So we have some problems with this. In order to solve it, we should test for each internal edge the orientation and take care of the signs. That's the main difficulty we have in implementation. Well, in order to test the problem, we consider an example posed on a inverted bell-shaped domain. We have a viscosity equal to 1 and no volume forces, and the prescribed velocity is 0, is set at the inlet where we have a vertical parabolic profile, and at the outlet where we have a horizontal parabolic profile. As finalization parameters, we took sigma E equal to 8 for every edge in the mesh, and this parameter alpha is the coefficient, the consistency term in the linear form. So we started the adaptive algorithm with an initial coarse mesh of 84 elements, and at every adaptive step, we unit the mesh using the adapt mesh function. And we control the shape regularity by running the gradient of the mesh size function. Here we can see the mesh after 9 iterations of the SIPG variant of the BD method, and you can see that the mesh is highly refined around the origin where the similarity occurs. We have tested also the other variants of the BD method, the IIPP variant and the NIPP variant, and the results are similar to what I'm going to show you. Here we can see the total error versus the number of degrees of freedom. Since in this case we don't know the exact solution, what we have done is to compare our output with the discrete solution obtained with the good failure method over a very fine mesh. The green line denotes the theoretical order of convergence, and you can observe that the red line, which is the value of convergence for the adaptive method, that the adaptive method converges faster than the uniform method. We also look at the behavior for the velocity and the pressure. So we have similar behavior, and we also plotted the indicator versus the degrees of freedom. And finally, we plotted the efficiency index, which is defined as the a posteriori error indicator over the total error. And for the adaptive algorithm, we can see that it approaches values without six. According to the theory, it should be bounded. In this case, well, the optimal value would be 1, but in this case, the results are pretty good. So, to conclude, we have a new posteriori error indicator, which is reliable and locally efficient for an enriched Galerkin method of order 1 for the Stokes problem. We implemented the adaptive algorithm in a parallel code with M++, and the numerical results confirm the reliability and efficiency of the indicator and the good performance of the adaptive algorithm. So that's all. Thank you very much for your attention.
So we have time for a question. So I'm co-author, so I don't have to. So
Well, we discussed it, but at this moment we are doing another thing. But definitely will be best.
I have a question on parameter epsilon.
Yes.
Coercivity may change by taking off the epsilon -1 or 1.
If there's some difference, you mean? For the numerical results, the behavior is the same.
Uh-huh.
But the difference is that the form A is symmetric or non-symmetric depending on the value of epsilon.
I see. So what is the advantage of the unsymmetric A?
What is?
the
What is
advantage.
advantage? Because original Stokes is symmetric.
Yeah, well, that's one advantage, and it has also advantage from a computational point of view. If the matrix is symmetric, so asymmetric, that will be smart.
Okay, thank you.
Okay. Just a remark on this problem. You have to be careful because you have two space for the velocity. And in fact, you have the constant and the velocity which appear in the two space. This is the only numerical problem when you code that. So you have to remove one velocity in one space to be